Right now, 4 astronauts are flying toward the moon through an invisible ocean of deadly radiation. They can't see it, they can't feel it, but it's there, bombarding their bodies with particles that could damage their DNA, increase their cancer risk, and affect their cognitive function. On Earth, we're protected. A magnetic field wraps around our planet like an invisible shield. Our atmosphere acts as a buffer. We live in a cocoon of safety that we take completely for granted. But the moment you leave Earth's protective embrace, that shield disappears, and the cosmos, beautiful, wonder-filled cosmos, becomes genuinely dangerous. This is the story of cosmic radiation. This is why space travel is harder than it looks. This is what every astronaut faces the moment they launch. Hey space family, welcome back to D3, Discover Deep Dreams, your educational gateway to the cosmos and beyond. I'm your co-captain, and today we're talking about something that doesn't get enough attention when we discuss space exploration, the radiation environment beyond Earth's protection. Artemis 2 is happening right now. 4 astronauts are on their way to the moon, and they're doing it while being exposed to radiation levels that would be considered dangerous on Earth. Understanding cosmic radiation isn't just fascinating, it's essential to understanding why space exploration is so challenging and why protecting our astronauts matters so much. So let's talk about what's trying to kill our space explorers and how we're fighting back. Cosmic radiation comes from 2 main sources, the sun and deep space. The sun constantly emits charged particles, mostly protons and electrons, in a stream called the solar wind. Under normal conditions, this solar wind is relatively mild, but occasionally the sun has a tantrum. A solar flare erupts. A coronal mass ejection, CME, blasts billions of tons of plasma into space. Suddenly, the radiation environment becomes significantly more dangerous. Beyond the solar wind, there's galactic cosmic radiation, high-energy particles that come from outside our solar system. These are mostly protons, but they include heavier nuclei as well. These particles travel at nearly the speed of light, carrying enormous amounts of energy. On Earth, we're protected from both of these radiation sources. Our magnetic field, the magnetosphere, deflects charged particles from the solar wind. Our atmosphere absorbs the particles that do get through. We're wrapped in layers of protection, but the moment you leave Earth orbit, those protections disappear. Imagine Earth surrounded by an invisible bubble. That bubble is the magnetosphere, a region of space shaped and controlled by Earth's magnetic field. The magnetosphere is created by Earth's liquid iron core, which generates a powerful magnetic field. This field extends tens of thousands of miles into space. It's invisible, but it's one of the most important things keeping us alive. When charged particles from the solar wind approach Earth, the magnetosphere deflects them. The particles follow the magnetic field lines, spiraling around them like water flowing around a rock in a stream. Most particles never reach Earth's surface. Some particles do get trapped in the magnetosphere. They spiral back and forth along magnetic field lines, creating what we call the Van Allen belts. These are regions of intense radiation trapped by Earth's magnetic field. They're so intense that we had to design special shielding for spacecraft that pass through them. But even the Van Allen belts are far less intense than the radiation environment beyond Earth's magnetosphere. The International Space Station orbits at about 250 miles altitude, still within the magnetosphere, still somewhat protected by Earth's magnetic field. Astronauts on the ISS receive elevated radiation doses compared to people on Earth, but they're still relatively protected. But Artemis 2 is different. The crew is traveling beyond the magnetosphere into deep space. They're heading to the moon, which is about 240,000 miles away. They're leaving Earth's protection behind. Once you're beyond the magnetosphere, you're exposed to the full force of cosmic radiation, solar wind particles, galactic cosmic rays, high-energy protons, heavy ions. All of it is bombarding you constantly. The radiation dose increases dramatically. Astronauts on the ISS might receive about 150 to 200 millisieverts of radiation per year. A sievert is a unit measuring radiation dose. That's elevated but manageable with protection and monitoring. But deep space missions, Astronauts can receive 1,000 millisieverts or more during a multi-week journey. That's 5 to 10 times higher than ISS levels. This is where it gets serious. Radiation damages cells by ionizing them, knocking electrons off atoms and creating charged particles that damage DNA. At low doses, the body can repair this damage. Your cells have repair mechanisms. They can fix broken DNA strands. Most of the time, these repairs work perfectly, but at higher doses, the damage overwhelms the repair systems. Cells die, mutations occur, cancer risk increases. For astronauts, the primary concerns are acute radiation sickness. At very high doses, over 1,000 millisieverts received acutely, astronauts could experience nausea, vomiting, fatigue, and potentially life-threatening conditions. This is unlikely on a lunar mission, but it's a consideration for longer, deep space missions. Increased cancer risk. Radiation exposure increases the lifetime risk of developing cancer. NASA estimates that a Mars mission could increase an astronaut's cancer risk by 1 to 3%. Not enormous, but significant. Cataracts. Radiation can damage the lens of the eye, leading to cataracts. This is a known risk for deep space astronauts. Cognitive effects. Some research suggests that high-energy particles passing through the brain could potentially affect cognitive function. This is still being studied. Central nervous system syndrome. At extremely high doses, radiation can damage the central nervous system directly. Again, unlikely on current missions, but a consideration for future deep space exploration. So, how do we protect astronauts from cosmic radiation? It's more complicated than you might think. Traditional shielding, thick lead or concrete, works well for some types of radiation, but it doesn't work as well for cosmic rays. In fact, adding too much shielding can sometimes make things worse. When high-energy cosmic rays hit dense shielding, they create secondary radiation that can be just as dangerous as the original particles. This is called the shielding paradox. More protection doesn't always mean safer. So spacecraft designers have to be clever. They use a combination of approaches, distance and time. The simplest protection is to minimize exposure time. Faster missions mean less time in the radiation environment. This is one reason NASA wants to develop faster propulsion systems for deep space travel. Shielding strategy. Rather than thick, dense shielding, spacecraft use layered materials chosen to absorb certain types of radiation without creating dangerous secondary particles. The Orion capsule on Artemis 2 uses specialized shielding in critical areas. Magnetic fields. Some proposals include using magnetic fields similar to Earth's Magnetosphere to deflect charged particles. This technology isn't mature yet, but it's being researched. Polyethylene and hydrogen-rich materials. Materials rich in hydrogen are particularly good at absorbing radiation. Water, polyethylene, and other hydrogen-containing materials provide good protection without creating dangerous secondary particles. Operational planning. Mission planners track solar activity. If a solar storm is predicted, astronauts can shelter in the most heavily shielded part of the spacecraft. They monitor radiation doses carefully and adjust mission plans if necessary. Right now, the Artemis 2 crew is experiencing cosmic radiation exposure. They're being monitored constantly. NASA has radiation dose limits for astronauts, and they're taking those limits seriously. The crew is protected by the Orion capsule's shielding. They're monitoring solar activity. If a significant solar storm occurred during their mission, they would shelter in the most protected part of the spacecraft. But they can't eliminate the risk entirely. They're accepting a known, calculated risk because the goal, returning humans to the moon, is worth it. This is part of what makes space exploration so remarkable. These 4 astronauts understand the dangers. They've trained extensively. They've accepted the risks. And they're doing it anyway because human exploration matters. The radiation they're receiving will increase their lifetime cancer risk slightly. They know this. They've accepted it because some things are worth the risk. Artemis 2 is a 10-day mission. Radiation exposure is significant but manageable. But what about Mars? A Mars mission would take 6 to 9 months each way, 18 months total. That's exposure to cosmic radiation for over a year. the accumulated dose would be substantial. This is one of the biggest challenges facing human Mars exploration. We need better shielding technology. We need faster propulsion systems. We need to understand the long-term effects of cosmic radiation on human physiology. Scientists are working on all of these fronts. There's research into active shielding using magnetic fields. There's work on faster propulsion, nuclear propulsion, ion drives, and other advanced systems. There's ongoing study of how human cells repair radiation damage. The goal is to make deep space missions safer, to reduce the risk to acceptable levels, to enable humans to explore Mars, the asteroid belt, and beyond, without accepting unacceptable health risks. Cosmic radiation is a hidden challenge in space exploration. It doesn't capture headlines like explosions or dramatic failures, but it's always there, it's always a consideration. Understanding cosmic radiation helps us understand why space is hard, why we can't just send people anywhere we want, why mission planning is so complex, why protecting astronauts requires constant vigilance and clever engineering. It also helps us appreciate what our planet gives us. Earth's magnetic field and atmosphere aren't just nice to have, they're essential for life. They protect us from constant bombardment by radiation that would damage our cells and increase disease risk. When you understand cosmic radiation, you understand why Earth is precious, why our protective layers matter, why returning to the Moon and eventually reaching Mars are accomplishments worthy of the risk and effort. Right now, Artemis 2 astronauts are flying through an invisible storm of radiation. They can't see it, they can't feel it, but it's there, and they're accepting that risk because exploration matters. This is the hidden cost of space travel, not the money, not the complexity, but the willingness to accept danger in pursuit of something greater. Cosmic radiation reminds us that space is genuinely dangerous. It's not a theme park, it's not a vacation destination. It's a harsh environment that demands respect, preparation, and courage. And that's what makes space exploration so beautiful. If you like space exploration, don't forget to like, subscribe, and ring that notification bell so you never miss a single D3 episode. Keep looking up.